So last lecture over gases. So we'll cover what's known as the kinetic theory of an ideal gas. So what are some basic properties of an ideal gas, and then just look at a few more applications. Okay, so what does it mean for a gas to be ideal? So first of all, if it's an ideal gas, that means it follows the equations. So the 7 equations we looked at: Boyle's law, Charles' law, Dalton's law, ideal gas law, the combined gas law, right? So if the gas is ideal, it follows those equations. So some gases follow those equations better than others. So these are the basic, so these 5 are the basic properties of an ideal gas. And so those are the gases that would follow those equations better. So first of all, so gas size is negligible compared to the distance between them. So basically that means, if that's a gas, the distance between them is huge compared to the size of the gas itself. So basically what this means is most of the space or volume in a gas is empty space, because the gas particles themselves take up very, very little volume. Gas molecules move in straight lines until they hit another gas molecule or atom or container or wall. So if that's a gas molecule, so basically they move in a straight line until they hit the wall, and then they bounce off, or they move in a straight line until they hit another gas molecule, and then they bounce off. So gas molecules move really fast, and they end up hitting a lot of things. So in reality, the motion of a gas molecule, maybe it looks something like that, but all of those turns are simply due to collisions. So otherwise, it's just flying in a straight line. Okay, so the attraction between gas molecules is weak or negligible, except for when they combine or when they collide. And so again, some gases follow this better than others. So if we looked at this example before. So if you had like helium versus ammonia, well, helium gases have very little attraction to other helium gases, right? Because they only experience van der Waals attractions, whereas ammonia, so it's really not true that they're only attracted to each other when they collide, because ammonia molecules will be attracted to each other all of the time, because hydrogens are partial positive and nitrogen's partial negative. So there's always an attraction between ammonia molecules. But the attraction is not strong enough for the molecule to be a solid or a liquid. But that's not true for something like water. Water is a pretty small molecule, just like ammonia, but water is a liquid at room temperature and 1 atmospheric pressure, because the attraction between water molecules is very substantial, because the hydrogen bonds are very strong. So water is a liquid at the same temperature and pressure that ammonia would be a gas. Okay, so basically, helium would follow the ideal gas laws better than ammonia would, because helium in this respect is more ideal than ammonia is, because there's less attractions between helium gas molecules. So collisions are elastic. So when 2 gases hit each other, then they just ricochet off of each other. So like a billiard ball, they just bounce off of each other. And again, some gases, this would be more true than other gases. So if you had 2 ammonia molecules, and again, the distance is huge between them in space, but when 2 ammonia molecules happen to collide with each other, they would have a greater tendency to stick because of those hydrogen bonding interactions. So in this regard too, helium's a better ideal gas than ammonia would be. And then lastly, the average kinetic energy. So if you know what kinetic energy is, it's basically the energy of motion, is proportional to temperature. So as temperature goes up, kinetic energy of the gas goes up, or as temperature goes down, then kinetic energy would go down. So basically, as temperature goes up, then the speed of the gas goes up. And you see this in the equation for the molecular speed of a gas. Right, where the equation, so temperature is in the numerator, so as temperature gets bigger, the molecular speed of the gas gets bigger. Okay, so lastly in this chapter, just a few more examples of these gas laws just from your everyday life that you should be somewhat familiar with. So if we take a soda can, for example, any carbonated beverage. So soda may typically be canned at 4 degrees Celsius and 1.1 atmosphere of pressure. So they basically pump CO2 into the beverage at a low temperature, higher pressure than atmospheric pressure. And then when that can comes to room temperature, what's going to happen as temperature goes up, pressure goes up, right? So that equation, P1 over T1 equals P2 over T2. So as temperature goes up, pressure goes up, Guy-Lussac's law. And so now you have a soda can at 20 degrees Celsius, and the pressure inside that can is going to be greater than when it was sealed. So now the pressure is about 2.47 atmosphere. And then what happens when you open the can? Well, you hear CO2 escape, right? Because when you open the can, now pressure goes down. Because it was at about 2.47 atmosphere, and now the pressure goes down to around 1 atmosphere, which is about atmospheric pressure. So what happens as pressure goes down? What happens to volume? Well, according to Boyle's law, right, pressure and volume are inversely proportional. So if pressure goes down, volume has to go up. So the volume at that CO2 is what's going to expand, and it's going to rush out of the can, which is the noise that you hear when you open the can. Okay, scuba diving has huge implications to gas laws. So at sea level, atmospheric pressure is 14.7 psi. So if you like to scuba dive, or if you ever want to scuba dive in the future, you have to be aware of gas laws. So if you dive 10 meters, so that's about 33 feet, then the pressure doubles. So at sea level, you're at 1 atmosphere of pressure, 14.7 psi. If every 10 meters that you dive, so every 10 meters that you dive, pressure goes up about 1 atmosphere. So if you dive 10 meters, 33 feet, now you're at 2 atmosphere pressure, so 29.4 psi. If you dive to 20 meters, so 66 feet, then you would be at about 3 atmosphere of pressure. So what happens as pressure goes up? So as you dive down, pressure goes up. What happens to volume? Volume goes down. So the volume in your lungs is being compressed. Well, where's the air in your lungs going? Well, it's going into your blood and it's going into your tissue. So, so basically more gases are being compressed into the tissues of your body if you dive deep. So what is the air? So what is in air? What is in air in a scuba diver tank? Well, that's nitrogen, of course, oxygen, primarily argon, the top 3 gases in the atmosphere. So as you dive, you're getting more nitrogen into the tissues, your oxygen into your tissues, more argon into your tissues. So this creates a problem when you resurface. So you must resurface slowly because as you resurface, then pressure is going down. So what happens to volume is if pressure goes down, according to Boyle's law, pressure and volume is inversely proportional, so volume's got to go up. So if you resurface too quickly, so if you dive deep, you have a lot of extra gases in your blood and in your tissue. And if you resurface too quickly, since volume is going up, can get bubbles. You could get bubbles in your blood, and that can be deadly. So you get what's called the bends. So anybody who scuba dives and they scuba dive deep, then they have to resurface slowly. So they basically would ascend about 10 feet, 3 meters, and they would stop and they would swim around there for a while. And that would give some time for the extra gases that are now coming back out to be exhaled. And then you would ascend another 10 feet, stop there and swim around for a while to give those extra gases that are coming back out of your tissues and blood to be exhaled. And that way one can avoid getting the bends, or even worse, to get in a bubble in one's blood, which could be deadly. So basically how airbags in a car work, according to gas laws. So if you take sodium azide and iron, so that would be iron 3 oxide. So basically 2 chemicals in an airbag, and then a collision causes those 2 chemicals to mix. And when these 2 chemicals mix, you make sodium oxide, elemental iron, and the one that's useful for an airbag is you make 9 moles of nitrogen gas. And so that's what inflates the airbag. So based on the number of grams of this you put in and the number of grams of that you put in, you could do stoichiometry, and you could use the ideal gas law to calculate the volume of the nitrogen gas that's going to be generated in that when those chemicals mix. So then you would know what the volume of that airbag would be when it inflates. Okay, and then lastly, gas laws are relevant to how hot air balloons work. So if you have a balloon, you have air molecules inside that balloon, and then you heat it up. So you start heating the gas, and so what happens when you heat the gas is they start moving. The gas molecules start moving faster, and then some of the gas molecules escape from the balloon, so they're moving so much faster now. So what you have now is you have fewer gas molecules inside the balloon. So same volume, but less air molecules, so the density of the air inside the balloon goes down. And if density goes down, then basically it becomes lighter, so to speak, and it's going to rise, right? So the less dense air will rise and causing the balloon to rise. And then if you want the balloon to come down, then basically you vent, you open up a vent, and some of the fast moving air molecules escape the balloon, and some slow moving gas molecules come into the balloon, and then eventually all of them have the same average speed, but the point is now you have more air molecules in the balloon, so the density of the air increases. And so the balloon descends in that case. So it's all relative to molecular speed of gases and density of air, causing the balloons to go up and down. Okay, so anyway, that's just a few applications of gas laws that I always find it. Chemistry is more interesting if you can look at some actual applications of the chemistry that you're learning, rather than just memorizing all of these formulas and how to do calculations and memorizing concepts. It's much more interesting if you can understand how those concepts are applied to your everyday life.